Hello guys, in the last video we wrote a program actually to check if the given number n is a prime number or not, and for that reason we like wrote our code in this way. Like we iterated over all these range from 2 to n minus 1 and checked like whether any of these number within this range divides the given number n completely or not. Like if we find a match, immediately we realized, like we display this output on the screen that the given number is not a prime number. However, if we exhaust the list completely and still we did not get a match, then at this point we display that the number is a prime number. Now in this video we are going to see in the last class what did we do is basically we started with this number 2 and we went, say we checked 3, then 4, and all the way up to n minus 1. Like this entire range we checked to determine whether that given number n is a prime number or not, that given number n is a prime number or not, right? So in this video what we will do is we'll try to see if there is that condition. Basically, you see that condition that we wrote in the while loop was like is less than or equal to n minus 1. That was the condition that we wrote. So it means, like, in the worst case, our program has to go almost n steps, right, to decide that number is a prime number. However, in this video, we'll try to see if we can reduce this range, like if we can reduce this number of steps. But at the same time, can we guarantee, like, say if we move only way up to this point, and then can we stop our search process here itself, so that we can guarantee that if the solution doesn't exist within this range, then the solution will not be there within this range. So that is something that we are looking for. Okay. Now let's start this point here, like an intuitive idea. Let's start with an intuitive idea. Say for example, we checked for this number 2 and then 3, and then we moved way up to this number, which is your n by 2, and then we still have to go for all these numbers, like n by 2 plus 1, n by 2 plus 2, like that up to n minus 1. We still have to go up to this. But suppose we checked up to this point, and then we up to this point, and then we saw that no number within this range from 2 to n by 2 divides this n completely. Okay, now can we stop the process here? See, what my point is, that we have checked, that is, there exists no such I such that n mod I equals 0, and I is I is less than or equal to n by 2. It means we have checked all these range and we didn't get a solution. That is, within this range, there exists no such I that completely divides this number n, right? So if we know that thing, can we conclude that the solution cannot be here in this range? That is our intuitive idea. Like intuitively you can say that the solution cannot be here. Actually, if up to n by 2 there is no solution, and there is a huge chance that the solution is not there in this range also. Now, how can we mathematically say that? Actually, okay, let's see. So we know that we know these things, right? That is, this is our ground truth. Like we know that we have checked all the number up to n by 2 and we didn't get a solution. That is, we didn't find any number I within this range that divides n completely. That is our ground truth. And also we know that, like, whatever this I is, now we are going to check that I is greater than n by 2. Okay, so these are our ground truth, and based on that, can we conclude something? Let's see. So say we assume that for some I which is greater than n by 2, we know that, like, I is greater than uh, n by 2. This is one of our ground truth, and this within this range there exists no such I that divides n completely. That is another ground truth. Okay, based on these two ground truths, what we can say, that, say for example, there exists an I which is greater than n by 2 and that divides n. So in that case, what will happen is that number I multiplied by, say for example, the other factor is k is equal to n. Okay, for some I which is greater than n by 2, we are assuming that this condition is true, that we are assuming that suppose there is a solution in this range, then this thing might be, this thing must be true. If there exists a solution in this range, then this thing must be true, right? I into k is equal to n. So if it is the case, then what we can say is that we can say that k must be equal to n divided by I, right? Okay, and then okay, that is okay, but still we cannot conclude anything from here. So, but we can do something here. Like, see here, if it is the case, then we can write like, okay, now if k is equal to n by I, then we can certainly write like k must be less than n divided by, no, n by 2. This n by 2, what am I doing is I'm replacing this I'm replacing this I by this n by 2. And why did I replace this equal symbol by less than symbol? uh, just to give you an idea, like, okay, intuitively again, say for example, you just assume that you have this n, some quantity that you want to distribute among some over a, over something, like that something is, say, over some number of people. So if you have more number of people, if you have more number of people like that, then each person will get some quantity. Say for example, the person gets some smaller quantity than n, like each person will get this much, right? But again, the same quantity, that same quantity n, now if you distribute over a smaller number of people, like only, a few, in that case, one thing intuitively should come into mind, that whatever that each individual will get, that quantity will be must be bigger than this previous quantity, right? This thing should be clear, isn't it? So that is what we have written here. Now see, this I initially it was bigger, like, see, because this is the condition that we wrote right here, that we know that our ground truth is that I is greater than n by 2. So here we have replaced this number, this I, by a smaller number, right? So if this thing is equal to this much, then this thing must be, since you are now dividing it by a smaller number, then the result will be a bit bigger. And that is why we replace that thing. Now this is bigger. Actually, this thing is bigger than this thing. Okay, and if the smaller thing was equal to k, then the bigger thing must be bigger than k. And that's why we have replaced that equal symbol by this less than symbol, right? So what is this then? Like k must be less than n by n by 2. So we can simplify it algebraically a bit. N by n by 2 can be written as n by n 2 multiplied. It means it must be less than 2. So it means what? Like, if we have reached up to this point, and if there has to be a solution within this range, then that number k must be less than 2. Okay, that is, that solution must be less than 2. Then when can we stop this process? Then when can we say that this solution, there cannot be any solution within this range? If we can say that, and at the same time, along with this ground truth, like at the same time, if we can say that n by 2, if n by 2 is greater than 2, then we can say that this number, there cannot be any solution within this given range. Like within, there cannot be any solution within this given range. So that's the thing. Now see, we can now, if you have followed up to this point, then we can, in general, we can write it in this way. Like we can stop the process, like say, now replace the thing, like can we stop it in one third? Like say we went to like 2, then 3, then say 4, then 4, and like that. Suppose we reach at some point of time like one third of n by 3. Okay, now can we, without looking at this portion, like up to n minus 1, can we stop the process? If we follow the same logic, then we can say that yes, we can stop the process as long as this n by 3 is greater than 3. Because see, here the same logic will be applied. Only thing is that instead of writing this n by 2, this 2 actually will be replaced by 3. Okay, everything is same. Like if there has to be a solution within this range where I is greater than n by 3, then that solution must be that n by 3 must be greater than 3. Like as long as, like as soon as we know this thing also, that is what are the two things that we need to know to stop the process here. That if we know that we have reached up to n by 3, if we reached up to this point, that is we have checked all these numbers within this range, we reach up to n by 3, and also we know that while reaching this point we already have crossed this n, that is we already checked, like there are no solution for this number, like less than 3. So it means that there cannot be any solution within this range. Okay, so this condition will be like if we apply up to this point, that is after checking each number, like every time we do this thing, like whenever we wrote there, like if n mod I is okay, I'll come to this point, but before that let's again make it more general. Like we know that, okay, um, you know um, this part actually, see here, if it is 3, then if we reach up to 3 n by 3, and then we know that like n by 3 is greater than 3, in that case we can stop this process. Similarly, we can say that if we reached up to n, this in general, so now replace this 3 by a general number, say for example k. If we have reached up to n by k, then we can stop the process if we know that n by k is actually greater than k. Okay, and then if we simplify it, we can write it in this way. This implies like n is greater than k squared. It means you can like k is less than, k square is less than n, or you can write like k is less than square root of n. So as long as the value of k is less than square root of n, this condition will be true. I mean, this condition will be true. As a result, we can stop the process. So what conclusion we can make? Like if the value of k, I mean this square root of n, like when it came out, like this square root of n, when it appeared on the screen, what conclusion we can make? That square root of n, like if we reached this point, like somewhere, like square root of, this is your n minus 1, this is your 2, and we checked all the number like 3, 4, 5, and way up to square root of n. We checked up to this point and there exists no solution here within this range. Okay, if there exists no solution on within the range of 2 to square root of n, then there cannot be any solution, there cannot be any solution within the range of n minus 1, square root of n to n minus 1. Right? Why you see for a moment, like see, if there exists a solution like this number, like we know the first thing is that we know that whatever the factors, if this n has a factor, then that factor is greater than square root of n, right? That factor must be greater than square root of n, because we manually check, like our program already checked up to square root of n, there is no solution. So if there has to be a solution, then the first factor must be greater than square root of n. And again, since there is no like factors which are less than square root of n, then the second factor also must be greater than square root of n. And in that way, if you like multiply two numbers which are greater than square root of n and square root of n, then certainly you will get a number which is greater than n. It means if there exists, I mean, here, if we assume that there is a factor here, like, two factors there of n, then if you multiply both these two factors, then you will exceed this range and you will get a number which is actually bigger than this n, like n plus something you will get, n plus something you will get. Like that is not something that we want. So we can conclude that if up to square root of n, if we have checked, and if we do not have a solution up to square root of n, then there is no chance that there will be a solution within the range square root of n to n minus 1. So we can immediately stop the process there. Let's write it in terms of code and check like what benefit it gives us. So this was our previous program, and there we checked whether this 7-digit number, 1, 2, 3, 4, 5, 6, 7, 8 digit number is a prime or not. Let's try with a 7-digit number. So this is a 7-digit number. I'm 1, 2, 3, 4. It is an 8-digit number. Let's pick one 7-digit number. I think 7-digit numbers were very fast, right? 1, 2, 3, 4, 5, 6, 7. Check. This 7-digit number I give, this is still the previous program. We have not checked any condition. We have not changed any condition till now. A 7-digit number I gave to the program, and it says that it is a prime number. It's very fast. Just to make things bit more, detectable. So I took a 8-digit number now. Say I take a 8-digit number, 1, 2, 3, 4, 5, 6, 7, 8, 8-digit number, 8-digit prime number, and I give this number to my program, and my program, let's see how much time my program takes, based on these conditions or based on this logic, to determine if the number is a prime or not. It is taking 6 seconds, 7 seconds, approximately 10, 12 seconds, 15 seconds might be. So it's a prime number, and it took approximately 17 seconds. Okay, and okay, for an 8-digit number, it is taking 15 seconds, with this condition, with this brute force approach. However, we just learned that we can actually write this condition. We can, instead of going way up to n-1, what we can do is we can stop our process in this, at the, like, as soon as we cross the square root of n limit, that is here in this picture. You should see that, as soon as we cross this square root of n, that is, if we know that up to this point, if we do not have a solution, there cannot be any solution within this range too. So if we have checked all the numbers up to square root of n, then there is no point of checking the numbers which are bigger than square root of n. That is, we can stop the search here itself and conclude that the number is a prime number. Let's do the change here. So if the value of I is less than or equal to square root of n, so square root of n means there is this function now, sqrt, square root of n. So I'll be telling you about this square root of n function, but for the time being, you just believe that this function gives you, this is a function that gives you the square root of a number. Okay, and this is already implemented in the computer. You can think it in that way. Now I is less than or equal to square root of that given number, and then, like, if this condition is false, it will go out of the loop. And here we can check, like, now see what is the first number that will violate this condition, because we need to know, like, whether the program has the control reached this point due to the by following this path or by following this path, right? And how do we know that thing? How can we verify that thing? Just by comparing the value of I with some number. And what is that number this time? That number will be, see here, if the control has to go out of the loop using this particular path, using this path, then the value of I must be, the first value of I that violates this condition will be greater than square root of n, right? So we have to check, like, if the value of I is up to equal to square root of n, it would have come inside the loop. So if the value of I is greater than square root of n, if the value of I is greater than square root of n, then we can conclude that, and we didn't get a match. It means, see here, if the value of I is greater than square root of n, it indicates that the control has reached this point via this particular path. It means what? There was no solution up to square root of n. That is, from 2 to square root of n, there was no solution. There was no number that completely divides this number n. So as a result, we can say that there cannot be any number from square root of n plus 1 to n-1. So as a result, we know that there is no such number within the range of 2 to n-1 that divides n completely. As a result, we can say that the number n is a prime number. Okay, now let's execute this program and check the output. Like, before executing this program, I want to tell you that if I execute, you'll get an error. Actually, you're getting an error that says that name square root is not defined. I mean, see, although I said you that there is a function that returns you the square root of a number, by simply writing it in this way, it will not be enough. See, you have to do something like this: import mat. Okay, and then you have to write here, Like not only square root, you have to write math dot square root, and here also you have to write math dot square root. Now, although I have not said you anything about this line, like what does this do, import math, but it should give you an intuitive idea that whenever I am doing like import something, you just assume that I'm bringing another, I'm bringing some pre-written code. I'm connecting some pre-written code with my program, and all those pre-written codes are there in this library. You can think it in this way, like math library. Math is a library where some functions are already written, or some codes are already been written by people. And so what we're doing is we're connecting our program to that particular library, and from that library we are using this function square root. And that function gives us the square root of a number. So till now you should understand this thing in this way, okay? But anyhow, if you use this Python more frequently, these sort of things will be quite obvious and familiar to you. Do not need to worry much about it, okay? But we are concentrating right now on the logic part of the program, okay? Now let's execute this program and check. See, it's a prime number. It's a prime number. Now see the difference. Previously, for these 8-digit number, it took us around like 14 seconds. Now this 8-digit number, it's now like the result is returned by the program instantly, almost like as soon as I click, I get the result. Even it will do much better if I give it here some 9 digits or 10 digits numbers. So let's try with a 9-digit number instead of jumping so much, like say 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 9-digit number. I pick any 9-digit prime number. Then let's see how much time does it take in a modified program. So it's a 9-digit number then. And let's say, and also it's very fast. See, it's very fast now. Like the previous program, when we tried with 9-digit number, it took us around like 2 minutes, right, if you remember. But here it is like very fast, and within seconds it is giving us the result. Even I can go for 10 digits number, so confident now that I can pick like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11-digit number. Let's pick this 11-digit number and see how much time does it take. Now directly jumping two more, like our problem size, our search space is now 100 times bigger, because see, magnitude of this number is 100 times bigger than our previous number. So let's see how much time does it take. No, it's damn fast. I mean, it's still giving us the result in a very fast way. Let's say now go up to 16-digit number. Let's pick one prime number here from here. I guess there are 16 or 17 digits in this number, and I put the number here, and let's say how much time does it take. It'll take some time this time, but it might get stuck also, because see, I have increased from 10 digit to 16 digit, almost like how much, 6 digits, by a huge factor. It might not turn out that the result will come, but okay, instead of doing it, we know that up to 10 digit it was giving us smooth result. Now stop it. I'm stopping the process, and instead of going like directly to 10 digits, 16 digits, let's try it something else. How many digits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 digits. I can be confident here a bit. So I can give this number 13 digits. Let's say how much time. Let's see how much time does it take. It's fast. 13 digit is okay. So maybe a 14 digit number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is a 14 digit number. How much time does it take? This is a 14 digit number, and it will take, see, magnitude is increased by 10 times. So it's still fast. 14 digit is still fast, right? So I can go up to 16 digit. It should not be that much of time. Say I give this number, and that is surprising, right? It's a nice prime number. All the digits are, oh, this 8 is there somewhere. I mean, just see this number. If you simply look at this number, you'll feel like, okay, this is not a prime number, but it turns out that it's a prime number actually. 4 seconds, 5 seconds, 6 seconds, 7 seconds, 8 seconds, 10 seconds. 11, 12. I mean, it's getting more and more. It's taking more and more time. I don't know when it will stop. 20 seconds. Surprising. 23 seconds. How many digits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 digits. So it might take me around 2 minutes or something. 17 digits I'm trying, okay? And after this, I'll try 16 digits. 17 digits and 16 digits. Like if the 17 digits number takes 100 seconds, then 16 digit number you can expect it will take you, um, 10 seconds or something, because the search space increases 10 times. More or less, an approximation of the thing. Certainly, I didn't do any rigorous mathematical checking on that comment, so don't take it for granted. It's taking too much of time. I mean, 1 minute, 17 seconds, and like that. I'd like to wait. Actually, I want to see how much time does it take. Two things actually: whether it gives us the right output, or and at the same time, how much time does it take to generate the output. For humans, certainly this is a huge number. I mean, to manually compute, like check, even if we have to go to after the square root of that number. So 1 minute, 49 51 seconds, approximately 2 minutes. I can assume that it might take. Okay, 1 minute 59, 2 minutes 1 second, and let's please come the result now. No, in a YouTube video, waiting for 2 minutes without doing anything, it's dangerous. But anyhow, after 2 minutes, 11 seconds, we got the result. Like, say, this number is one digit, two digit, three digit, four digit, five digit, six digit, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 digits number. Now, our program has given us the output for a 17 digits number, this version of the program, in 2 minutes, 11 seconds. Whereas in the previous logic, using the previous logic, in a 9 digit number actually took us almost the same amount of time. Now see, almost we are now, see, the search space has been now increased by a huge factor. But again, more or less, see, now we can compute, with this better logic we can compute, we can check bigger numbers whether they are prime or not, like in less amount of time. So now the question is there a better solution than this one? Yeah, there might be. You have to actually think rigorously in terms of mathematics, and if you can come up with an idea using tricks in mathematics, then certainly there could be one. Although I do not like claim in either way that there could be one, there might be one, there might not be one. Okay, so that is a different area now. Like, we'll not get into that part of the things. Okay. So up to this point, we'll stop the process here. Like, okay, well, for to check if the given number is prime or not, what we learned is that checking up to square root of n is enough actually to decide whether that given number is prime or not. And even it turned out that it is much faster than the brute force approach. Okay, guys, I hope you people enjoyed the video. Let's see you in the next video.